we are going to discuss few questions, and these questions will be from basically, you can say all of them will be based on this yo-yo concept. Okay, and along with the rotational, then there will be also the frictional forces that will be involved, some torque will be involved in it. Okay, so, but entire question discussion will be only for this yo-yo type of questions. So first question, a yo-yo of mass m consists of an axle of radius b and a spool of radius r. Its moment of inertia about its central axis is mr square by 2. The yo-yo is placed upright on a horizontal surface and a horizontal force F is applied to the string. The coefficient of friction between the yo-yo and the surface is mu. Determine the maximum value of the force F for which the yo-yo rolls without slipping on the surface. So based on this, we can just draw its basic figure. So we are given a yo-yo. It means there will be a outer part and there will be inner part, and the inner part is somewhat acting like an axle, and on which this outer part is going to rotate. And this is the surface, and we are given that B is the radius of the inner one and R is the radius of the outer part, and we have a thread on which a force F is being applied. Okay, so force F is being applied to this end, and because of this, in this type of question we have to remember one thing, that the point of contact in case of this yo-yo is different to the application of the force. Application force is applied on the inner part, or which is a thread is wound on the inner part, so we apply the force on that, whereas the frictional force is going to act as the outer part. Okay, so this we have to remember. So let us assume that P is the point of contact, okay, and so based on this, the frictional force, let us suppose that is of F, and there will be mg acting in the downward direction, and there will be also a normal which will be acting in upward direction. And let us assume that there is a linear acceleration A along the direction of the force. Okay. And so we have to make the equation, equation based on two things. First will be the translational equation, and second one will be our rotational equation. Okay. Rotational equation will be because of the torque, and the translational equation will be only because of the force. Okay. So these two equations we are going to write. So first we start with our translational equation. And translational equation gives us that the force minus frictional force will be equal to mass into acceleration. And next we can say that there will be a rotational equation, And for the rotational equation, we are having two forces. One is the applied force F and another one is the frictional force F. Okay. So we are going to have two torques. So first will be torque due to the friction. Let us call this as tau F, and that will equal frictional force multiplied by the radius r. And next will be our torque due to the applied force. Due to force F, and let us call this as tau F, and that will be equal to our F multiplied by B. Okay. And so one will be our clockwise, other one will be our counterclockwise. Okay. So therefore we can write the equation that the equation will be equal to our Fr minus Fb will be equal to I multiplied by angular acceleration, that's our alpha. And moment of inertia is given to us, that is our half m r square. And for our alpha, we can write, because there is a rolling without slipping, so alpha will be equal to A upon R. So this A square goes by R. So we get from here, it will be equal to our half mr times alpha. And so let us find out A from the first equation, that A will be equal to F minus upon M. Okay. And we substitute, sorry, here it is A, not alpha. So substituting A, acceleration, in this equation, we get this as our Fr minus Fp will be equal to half m, and A is our F minus small f divided by m. And here this m and m cancels out, and one thing is missing, r is missing. So we get from here half Rf minus half R frictional F, and we can just move them left to right. So we get this as Fr plus half R times F is equal to half Rf plus F times B. And this can be further written as, we can take F as common, we get this as R plus R by 2, and will be equal to F from the right side, so this comes as R by 2 plus B. Okay. So on our, this will be giving us F, and this will be 3 by 2 times R is equal to F R by 2 plus B. Therefore we get our frictional force will be equal to over F times R by 2 plus B divided by 3 by 2 times R. Okay, now it is a simple calculation. We can just separate the variables. So we are going to get this as F, and this will be R by 2, 3 by 2 times R plus B, 3 by 2 times R. And here R 1 by 2 cancels out, so we get our frictional force F will be equal to F times 1 by 3 plus 2B times 3R. Okay. And we have to find out the maximum force, and from the basic of our frictional force we can say that for maximum F, our value of frictional force will be equal to mu mg. Therefore, in place of our friction we can write mu mg. So we get this as mu mg will be equal to F, and we have 1 by 3 plus twice B divided by 3 times R. And so from here we get our F will be equal to, and we can take 3R will be our LCM. So this will be coming as 3 mu R mg, and in the denominator we are going to get R plus R is LCM, R plus 2B. Okay. So this is our maximum value of the force. Okay. We can slightly modify the same question. In this case, basically our that yo-yo was vertical, and if we assume that our yo-yo is in the horizontal position, so which basically means that if we look towards from the top side, our yo-yo is lying as a horizontal on the surface. Okay. And everything will be same except the, you can say, the frictional force. Okay, and so let me rephrase the question first, then I come to the diagram part. Okay. So we assume that our yo-yo is lying horizontal on the table. Lying horizontal on the table, which basically means that our axis is perpendicular to the table. Axis is perpendicular to the table. Okay. And F will be parallel to the table. F means applied force, and we can say F is applied parallel to the table. Okay. And so the force is more or less, we can say, the same, because in the first case also the force was parallel. Now the only difference is that the yo-yo is lying horizontally on the table. Okay. And in this case the yo-yo was such that its axis was parallel to the table. Okay. So if we draw the figure, so we can say the figure, we can just draw it like this, and this will be its center, and the table will be something like this. Okay, so it is lying horizontally on the table, and the axis will be perpendicular to table. So this is the axis. So inner radius once again is our B, outer radius is our R, and it is being pulled by same force F. Okay, that is no change in this thing. Now if we are seeing the yo-yo, we can clearly see that the wheel which rotates is of slightly larger radius as compared to inner one. From the figure also, the B is much smaller as compared to R. Therefore, the contact point will be the spool edge. This is called, the outer portion is called the spool. So the contact will be only this edge will be contact. Therefore, we can say that contact point is at the spool edge. And first of all, let's find out what will be the key difference between the first question and this question. Okay. So key differences, first of all, will be our rolling constraint. Rolling constraint, it means that our acceleration A will be equal to B multiplied by our alpha, okay, not the R. So this is the first key difference. And the second difference will be that the friction acts at we can say at R from the axis. This is in the first case also it was same, but now it will be the entire portion of the circle. Okay. So we can say this will be our spool edge contacts the table. And next will be same. There is, so the main difference is the rolling constraint, that A is equal to B times alpha, and these two are similar to our first part. Okay. And the force is applied at B from the axis, which is same, or we can say our pull acts at B from the axis. And once again, there will be two types of motion. One will be a translational and other one will be a rotational. Therefore, we can write that our translational will be giving us F minus F is equal to M times A, and from here once again our A will be equal to F minus small f divided by M. And next is our rotational. And rotational, we have two torques. One is our frictional torque and other one is our pull torque. Okay. So for rotational, we have our frictional torque, that is our friction multiplied by the radius, and then we have a pull torque or force torque, and that is equal to our force multiplied by the radius. Inner one is B. One is our clockwise, other one will be our counterclockwise. Therefore, you can write that our F times R, Fb is equal to I times alpha. So this comes as half m R square, and this will be A divided by B. So this is the only major difference. Okay. And we substitute value of A, we get this as our half mr square upon B, and A is our F minus divided by M. And here this mass and mass cancels out, therefore we get Fr minus Fb will be equal to, we get this from R square by 2B, and we have F minus F. And this is now part of calculation, rest is are solved. So we multiply our left side, so we get this as our 2BFR minus 2FB square is equal to Fr square minus frictional force R square. And now we can just interchange them, and we get this as our 2 times Fr plus Fr square is equal to Fr square plus 2 times Fb square. And from here we can take frictional force as common, so we get this as twice B times R plus R square, and one second, F, this is our 2BF, yeah. So from here we can take F as common, so this comes as our R square plus 2B square, and this gives us that value of frictional force will be equal to F, and this is our 2BR plus R square, and divided by R square plus, sorry, reverse. So we get this as our F, numerator will be our R square plus 2B square, and denominator will be 2BR plus R square. Similarly, for our maximum friction, we can substitute this F by mu mg, so we get this as mu mg is equal to, this will be F, and from the denominator we can take R as common, but that is not required. Okay, we can keep it as it is, and so this comes as a F, and R square plus 2B square, and this is 2BR plus R square. Therefore now it is F max is equal to, we have this as mu mg, and this comes as our 2BR plus R square, and we have r square plus 2b square. Okay, rest of the things will be same except the value of our constraint motion. That's the only difference. Next question. It states that a yo-yo of mass m has an axial radius of b and a spool radius of r. Its moment of inertia can be taken as, one second, okay, I forgot to, there is another part to it. Yeah, so I forgot to mention that we can also consider that if force F is being applied at an angle of theta with respect to the horizontal. Okay. So it means that this is the outer one and we have a inner part, and this is a surface, and this is the horizontal one, okay, throughout like this, and a force F is being applied at angle of theta with respect to the horizontal. The rest of the things are same. So we have inner radius b, outer radius our r, and same calculation. So we have our frictional force F, and in the downward we are going to have our mg, and in the upward we are going to have a normal. Okay. So these things are same. And so once again, this F we can divide into two components. Okay. So we get one component will be our F cos of theta, and other component will be our F sine of theta. So therefore, because we can use the vertical equilibrium, okay, so we start with our equilibrium equations. Equilibrium equation, and first is our vertical equilibrium. And in vertical equilibrium, there is no vertical acceleration. Okay, entire the moment of this yo-yo is in the horizontal plane, horizontal direction, or we can say in x direction. So this is our x, and we have in y. So we can say that our summation of forces in y direction will be equal to 0. So based on this, we can say that our n plus f sine of theta and minus mg will be equal to 0. And from here we can write that our normal n will be equal to mg minus f sine of theta. Let us call this equation number 1. And next is our torque equilibrium. Torque balance, okay, and therefore we can say that under the torque balance condition, you can say the summation of the torque is equal to 0, or we can say that the torque due to our applied force plus or minus, we can just later on change it, and torque due to frictional force is equal to 0. Okay. And if we consider its directions, let me put the values. So we have a torque because of the frictional force, that is our R times F, and the torque due to our applied force, their sum will be equal to 0. And from here we can say that our frictional force is equal to Bf upon R. Let us call this equation number 2. And for the, you can say, the static limiting condition, or we can say on the verge of slipping, so we can say our static friction limiting condition, or we can also say on the verge of slipping, on the verge of slipping. So under this condition, we know that the frictional force achieves a maximum static value on the just on the verge of slipping. So we can say that the frictional force achieves its maximum static value therefore we can say that our friction will be equal to mu times n, and our friction is our Bf upon R, and we also know our n. So from equation 1 and 2, from 1 and 2, our frictional force is our B upon R times F. This comes as mu, and our n is our mg minus F sine of theta. And we have to solve it for theta. So we can say that our mu F sine of theta will be equal to our mu mg minus Bf upon R. Okay. And from here we can say that our sine of theta is equal to mu mg divided by mu f minus Bf, and this is our R times mu f. So from here our mu and the second part force cancels out, therefore we get our sine of theta will be equal to mg by f minus B upon mu times R. Okay. And I forgot to mention at the start that we have to find out the maximum value of theta. Okay. We have to find out the maximum value of theta for which it is just about to you can say move. So this theta we can call it as a threshold angle. Therefore we have taken the torque is equal to 0 because it is not yet moving, it is on the verge of moving, okay, rolling without slipping. Therefore we can say that the threshold angle threshold angle at which torque balance can be maintained so we can say our sine of theta max will be equal to mg upon f minus b upon mu r. There is another question that is based on this, and that is we have to find out the various, you can say, because as theta is going to vary, the yo-yo will be moving in the forward direction, and it can be also moved towards reverse direction, backward direction, depending upon the value of theta. We will do that later on. That is a separate question. Okay. And from this theta max, we can also find out our maximum value of the f max for a given theta. And so once again, we start with our, so we can say maximum force for given value of theta, and for that we once again start with our bf upon r is equal to mu mg minus mu f sine of theta. Okay. So here we are going to find out the value of f. So f we can just move toward our left side, and we can take f as common, so that will be coming as b upon r, and this comes as mu sine of theta, and that will be equal to over mu mg. Okay. So we can say that value of f will be equal to mu mg, and this will be b upon r plus mu sine of theta. And so we can say that the maximum value of the pull that will still allow the torque balance without slipping. So we can say the maximum value of f, we can write this equal to over f max, which allows torque balance. So we can replace our f by f max, and rest of the things are going to remain same. So we can say our f max will be equal to mu mg, and this is b upon r plus mu sine of theta. And we can also find out the force when there will be the yo-yo will lift from the ground, okay, from the surface. And for that we can say the condition for liftoff, and condition for liftoff means the yo-yo loses the contact with the ground, and liftoff under this condition, obviously the value of normal will be equal to 0. So we start with our basic equation, that is our n is equal to our mg minus f sine of theta, and we put normal is equal to 0. So we got 0 is equal to mg minus f sine of theta, and for when the normal is 0, let us call this as f as lift, f lift. Therefore we can write that our f lift will be equal to mg upon sine of theta. So this is the force of our liftoff. Okay, now come to the next question. It states that a yo-yo of mass m has an axle of radius b, a spool of radius r. Its moment of inertia can be taken as half mr square. The thickness of the string can be neglected. The yo-yo is released from rest. There are two parts. Find the tension in the string as the yo-yo descends and at its ascends. Part B. The center of the yo-yo descends at a distance h before the string is fully unwound. Assuming the yo-yo reverses the direction with uniform spin velocity, find the average force on the string while the yo-yo turns around. Okay, so based on this, we have two parts. In the first, we have that the yo-yo is ascending and descending, and in both the cases we have to find out the tension. Okay. So we can say that we can just draw a approximate figure. So we have a inner, and this is center, b is the radius, and r is the radius of the outer part, and in this case suppose T is the tension, and let us call this as TA, that is T descends. Okay, when this yo-yo is moving in the downward direction, and there will be mg acting in downward direction, and let us assume that it is rotating with the angular speed of alpha and moving with the acceleration a in the downward direction. Okay, we are going to solve this part, that we have descending part, and then we come back to our ascending part. Okay. So this is our descending. Therefore, we can write that our equation for our motion, it can be written as our mg minus tension descending will be equal to mass into acceleration. Okay. And there will be a torque because of this tension, and okay, let me rephrase it differently. So in case of descending, let us write it as a vertical force balance. Vertical force balance. And we can say now I have mg minus td is equal to ma. And there will be also our rotation. Now, so we can say the rotational, or we can say rotational. You can say rotational dynamics, and this rotational dynamics is going to give us a torque, that is our so rotational dynamics is going to give us a torque, and let us suppose that torque is our tau, and this is our tau d descending, and that will be equal to our tb, and that is going to give us moment of inertia and its angular acceleration. And we have a rolling constraint also. Rolling constraint, and that rolling constraint is equal to linear acceleration A is equal to B times our alpha. Okay. So from here we can say that our alpha is equal to B upon A. Alpha is equal to A upon B. Therefore we can substitute in this equation. So we get this as our TB, and I also we know is our half mr square, and alpha is our A upon B, and here tension is our TD, tension descending. So this is our TD. Therefore from here we can say that our tension descending will be equal to our half mr square multiplied by A upon B square, and tension descending is our MA so we can use this equation. Let us call this equation number 1. So from equation 1, we get mg minus half mr square A upon B square is equal to m multiplied by A, and we can combine these A terms. So we get this our mg is equal to A we can take as common, so this comes as our m plus, and we have here, one second, yeah, so we have this as half mr square upon B square, half mr square. A we have taken common, okay, and from here we can write that our A will be equal to mg, and this comes as m, or we can take m as also common. Okay, let us take m as common, so this becomes 1 plus 1 by 2 r square upon B square, and this m and m cancels out, so this comes as our g, and we have 1 plus 1 by 2 r square upon B square, and we found out our acceleration. And once again we use our first equation and we substitute value of acceleration. Okay. Therefore we can say from equation 1 we can write our T descending will be equal to mg minus ma, and we substitute our A, so we get this our T descending will be equal to, we have this our mg minus, this also comes our mg 1 plus 1 by 2 r square upon B square, and we can take our mg as common, or okay, let's take mg as common, so So this comes 1 minus 1 upon 1 plus 1 by 2 b square upon r square upon b square. And let us take the LCM. So we get a descending is equal to mg, and it comes as 1 plus 1 by 2 r square upon b square, and this comes as 1 plus 1 by 2 r square upon b square minus 1. Plus 1 and minus 1 cancels out, and in this term in the denominator we can also take our LCM, so that is going to sort it. So LCM will be our 2b square, so this comes as our 2b square plus r square, and 2b square and this 2b square is going to cancel out each other, so we get this as mg r square. R square. So this is the tension during the descent. Okay. And now we come to ascending part. So we have ascending phase, and first thing that is going to change is the direction of our acceleration. Therefore we can say the acceleration due to ascent will be equal to minus of the acceleration during the descent. Okay. Therefore we can write the equation that our equation number 1, which was our t minus mg, and this comes as our m and our a ascent. Okay, because now I can draw an approximate one. Okay, so we have our tension T and we have our mg in the downward direction. Okay, and this is a ascent, so let us call this as TA, and this is also our TA. And previous acceleration in the first case was in the downward direction, which was a, and in this case the acceleration will be one upward direction, which we have assumed as a ascent. So obviously the relationship between them is the a ascent is equal to negative of a. Therefore if we substitute a ascent as negative of a, so from here we get that m is equal to minus of a. We can write tension ascent minus mg is equal to minus of ma. Okay. And this equation we can write that our TA is equal to mg minus ma. So if you look closely, this equation is same as our this equation. Okay, let me write it from equation 1. From equation 1 we have our mg minus t descent is equal to ma, and from here we can write our t descent is equal to mg minus ma. So these two equations are our same. Therefore we can say that our tension during ascent will be equal to tension during descent, which will be our mg r square and 2b square r. Mg r square 2b square plus r square. So even tension will be equal, but the acceleration is going to change the sign. Okay. So this is the, and we come to its B part, and B part states that it descends by a distance of h, and the string is fully unwound rather, and it moves reverse its direction with the same uniform spin velocity. We have to find out the average force on the string. Okay. So we come to part B, and here, because the yo-yo is going to stop suddenly, so there will be an impulse force acting on the string. Okay, so that's why we can call this as a velocity and impulse. And first of all, let's assume that our yo-yo is okay. So here it is moving, suppose, in the downward direction with the velocity of vf, and all of a sudden it is going to reverse its direction and move in the upward direction with the same velocity, that is of vf. And we can say that it started from this height and the string is completely unwound. Okay. So here the string is completely unwound, and this is given as our h. So this is our initial position and this is our final position. So we can say that the center velocity changes from vf downward to vf upward. Therefore the change in momentum, that is our delta p, will be equal to m, and this will be our vf minus of minus vf, and this will be giving us twice m vf. And this change in momentum can be also written as, suppose there is a string force, that is, we call this as f string, and that is applied for a fraction of a second, that is a delta t, and that will be our change in momentum, or we can say it will be equal to twice m vf. Okay. And in this case we have to find out this value of delta t, which is nothing but time of reversal. And time of reversal, and in this case there is a basic concept on which this time of reversal is based, because the reversal is obviously going to happen at the bottom. It means at the final position the reversal is going to take place, and the spin velocity in the question it is mentioned that it is going to remain same. Okay. And for this fraction of second there will be, you can say, no torque changing the rotation because of during this brief phase. And this turnaround means the change in the direction of the spin from the ascend to from descend to ascend is going to take place at half rotation, that is our pi radian. Okay, so we have to remember this basic thing here. Okay, it is a little bit tricky, but this is the basic of this yo-yo, that the turnaround turnaround happens over a half rotation. Full rotation is our 2 pi and this half rotation is our pi radians. So based on this, we can say that our omega multiplied by delta t will be equal to over pi, and from here we can say that our delta t will be equal to pi upon omega, and we can use our rolling condition, that is our Vf is equal to b times omega. Therefore we can write the equation, that is our f string multiplied by, let me write it here, so we have our f string multiplied by delta of t, and that is equal to 2m Vf. So we can say from here that our f string will be equal to Vf, we can write this as 2m Vw, and delta t is our pi upon omega. Therefore we get this f string will be equal to 2m b omega square upon pi. So this is our string, and now we can use our conservation of energy and find out the value of omega square and substitute here. Okay, so we can say our conservation of energy and at initial position there is only potential energy, whereas our final position it is going to have the translational as well as the rotational energy. So we can say our initial potential energy will be equal to our mgh, and our final kinetic energy this final kinetic energy will be equal to translational plus rotational. And so we substitute this and we get it as half m Vf square plus half I omega square, and Vf we already know is our, so we can say this will half m, and Vf is our b times omega whole square plus half moment of inertia we also know is our half m r square and times omega square. So we get this will be equal to our half m, and we can take our omega square as common, so this will be our b square plus 1 by 4 mr square times omega square, and through the conservation this will be equal to our mgh. Therefore from here we can say that our m we can just cancel out, so we can say that our omega square will be equal to we have our GH, and this will be B square upon 2 plus R square upon 4. We can take the LCM. So we get our 4 as LCM, so this will be our 4GH, and we get this as a 2B square plus R square. So we substitute the value of our omega square in our F string. So we can say force on the string will be equal to, we were having it as 2mb upon pi, 2mb upon pi multiplied by 4gh 2b square plus r square. So this is our value of our average force. Okay, so this is our average force. Average force. Only tricky part is about this half rotation. Okay, and that half rotation is going to take place with the fraction of second, that is our fraction of time rather, that is delta t. Next question. Okay, this is the question which I was talking about. So a yo-yo is pulled along a horizontal surface by means of a string without